The vibration period of a building plays a crucial role in how it responds to an earthquake. This period represents the time it takes for the structure to complete one full oscillation back and forth when subjected to seismic forces. Just like a swing, the taller and more flexible a building is, the longer its vibration period will be. When the natural vibration period of a building closely matches the predominant period of an earthquake, a dangerous phenomenon called resonance occurs, amplifying the building's movement and increasing the risk of severe structural damage or even collapse. An 11-story building typically has a natural vibration period of around 0.8 to 1.5 seconds. This means that during an earthquake, if the ground motion shakes with a similar period, the building will sway excessively. Earthquakes do not shake the ground at random, they generate waves with specific frequencies and predominant periods depending on their magnitude, depth, and local geological conditions. For instance, a powerful earthquake of magnitude greater than 7.0 may produce ground motions with predominant periods of 1 to 3 seconds, while smaller earthquakes, magnitude below 6.0, typically generate shorter predominant periods, between 0.1 and 1 second. If the seismic waves of a large earthquake have a period close to 1.5 seconds, they can cause dangerous resonance in an 11-story building, dramatically increasing the forces acting on it. The type of soil beneath a building significantly affects how it responds to seismic waves. Hard, rocky soil transmits earthquake energy quickly, leading to rapid ground movements with short periods of 0.1 to 0.5 seconds. On the other hand, soft, loose soil slows down seismic waves, prolonging the shaking and increasing its amplitude, often with predominant periods of 1 to 2 seconds. In areas near lakes, rivers, or locations with water-saturated soil, the situation becomes even more critical. Liquefaction can occur, turning solid ground into a fluid-like state, causing buildings to tilt or even collapse. If an 11-story building is constructed on soft soil, it becomes even more vulnerable to resonance. As the extended shaking period aligns with the building's natural period, buildings of different heights respond differently to earthquakes. An 8-story building, for example, has a shorter natural period, typically between 0.6 and 1.2 seconds. This means that while it might not be as affected by large earthquakes with long predominant periods, it could resonate with moderate earthquakes that generate shorter period seismic waves. Smaller buildings, such as those with 3 to 5 stories, have even shorter periods and are more susceptible to high-frequency ground motions, usually produced by smaller earthquakes. Understanding these relationships is essential for engineers to design structures that minimize seismic risk. History has shown us how resonance can lead to catastrophic building failures. One of the most well-known cases occurred during the 1985 Mexico City earthquake, where the soft clay soil significantly amplified the ground shaking for buildings between 10 and 15 stories tall. Many of these structures collapsed because their natural periods matched the prolonged seismic waves. Similar destruction has been observed in Turkey, Japan, and other earthquake-prone regions, highlighting the importance of designing buildings with seismic resistance in mind. To mitigate the risks associated with resonance, engineers employ various techniques to modify a building's response to earthquakes. One effective solution is the use of seismic base isolators, which allow the building to move independently of the ground, reducing the amount of seismic energy transferred to the structure. Another approach is the installation of vibration dampers, which absorb and dissipate energy, preventing excessive movement. Additionally, modifying the building's stiffness by adjusting materials, adding structural reinforcements, or altering the shape of the structure can shift its natural period, reducing the likelihood of resonance with earthquake waves. For existing buildings that were not originally designed with seismic safety in mind, retrofitting is necessary to enhance their resistance. Engineers can add bracing systems that provide extra stability, strengthen foundations to minimize the effects of soft soil, or install dampers to control oscillations. These measures help ensure that buildings remain standing during strong earthquakes, protecting both occupants and infrastructure. Understanding the relationship between a building's vibration period and an earthquake's predominant period is crucial for constructing safe structures. By analyzing soil conditions, seismic risks, and the natural periods of buildings, engineers can design and reinforce structures to withstand earthquakes without falling into resonance. In earthquake-prone areas, proactive planning and proper engineering solutions are essential to minimizing destruction and saving lives.